In this lecture, we're going to talk about acids, bases, and chemical equilibrium and buffers. So acids in, day-to-day life, we consider them being sour. Citrus fruits contain a lot of acids, but chemically, acids can be defined as Arrhenius acids or Bronsted-Lowry acids. There's another class called Lewis acids, but we're not going to talk about them. So Arrhenius acids are compounds that produce hydrogen ions, and these compounds are dissolved in water. For example, hydrochloric acid dissociates into hydrogen ion and chloride anion. Since they produce ions in the water solutions, they are also electrolytes. Solutions of acids usually have a sour taste. They turn the indicator litmus, which is blue, they turn it red, and acids can corrode certain metals. Acids which contain a hydrogen ion and a nonmetal are named using the following rule. Use the prefix hydro, then the name of the nonmetal ending with IC. You use first syllable, so hydrochloric acid, hydrobromic acid, hydroiodic acid. For Cn negative, it's hydrocyanic acid. Acids which contain a hydrogen ion and a polyatomic ion, usually named by changing the end of the name of the polyatomic ion from ate to IC and from ite to OUS. So chlorate, ate is changed into chloric acid. Sulfate will be sulfuric acid. Chlorite will be chlorous acid. Nitrite will be nitrous acid. So these are some names. There's a lot of memorization you will have to memorize. You will find certain patterns here, so please remember these acids. Arrhenius bases are compounds that produce hydroxide ions when they're dissolved in water. If you taste them, which I suggest you don't, but they taste bitter or chalky. Since they produce ions when dissolved in water, they are also electrolytes. Between the fingers, they feel soapy and slippery, and red litmus indicator paper will be turned blue, while phenolphthalein indicator will be turned pink. Now, typical Arrhenius bases are named hydroxides, so sodium hydroxide, potassium hydroxide, barium hydroxide, aluminum hydroxide. Here you can see calcium hydroxide used as a filler in the root canals. Now, Bronsted-Lowry acids and bases are a little different. An acid is a substance that donates hydrogen. So you can see that all Arrhenius acids are automatically become Bronsted-Lowry acids. The base is a substance that can accept hydrogen, and as we will see pretty soon, all Arrhenius bases are also Bronsted-Lowry bases. So for example, water can easily accept hydrogen, becoming hydronium acid, which makes water in this reaction, water is a base and hydrochloric acid is an acid. Now in reaction between ammonia and water, you have two true Bronsted-Lowry acids and bases. So ammonia acts as the hydrogen ion acceptor, thus becoming a Bronsted-Lowry base, while water acts as hydrogen ion donor, thus becoming Bronsted-Lowry acid. And at the end of the day, you have a basic solution with ammonium ion that is protonated and hydroxide ion. So these are some comparative characteristics of acids, bases, according to Arrhenius and Bronsted-Lowry. Know these features, know the responses of various indicators. So when acid and base react, there are two conjugate acid-base pairs formed. So each pair is related to each other by loss and gain of hydrogen ion. So one conjugate base happens in the forward reaction direction and another happens in the reverse direction. So for example, in this hypothetical situation, HA and A represent one conjugate base pair and BH and B represent another conjugate acid-base pair. So for instance, when hydrofluoric acid interacts with water, donates hydrogen to water. Thus, hydrofluoric acid and fluoride anion form one conjugate acid-base pair. Hydronium ion and water form a second conjugate acid-base pair, where hydronium anion is conjugate acid and water is conjugate base. And you can see that each pair is related by loss and gain of hydrogen ion. You should be able to identify the conjugate acid-base pair in the reaction. For instance, in the reaction between ammonium and water, ammonium and ammonium cation is one conjugate acid-base pair, and water and hydroxide ion in another is another conjugate acid-base pair. Acids and bases can be characterized by difference in strength. So strong acids and bases completely dissociate in water. Weak acids and bases only partially dissociate in water. For example, hydrofluoric acid is the only halogen acid that is a weak acid. So let's talk about strong and weak acids. Strong acid completely ionizes in aqueous solution. So hydrochloric acid, for instance, completely dissociates into hydronium ions and chloride anions. The weak acid, such as carbonic acid, when it interacts with water, forms few ions, hydronium ions, few bicarbonate ions, but most of it exists in the molecular form. So, for instance, hydroiodic acid, when it dissolved in water, completely dissociates into hydronium ions and iodide. And there are 6 common strong acids. You need to know all 6 of them. And when they dissociate, the conjugate base is considered to be weak base. It is a general rule. The conjugate base of a strong acid is weak. If you're interested, the conjugate base of the weak acid, it's not super strong, but it's kind of stronger. So in weak acids, only few molecules dissociate, resulting in few ions, hydronium ion and fluoride anion, but most of the acid exists in the molecular form. So most acids are weak, and the conjugate bases are considered to be strong. So if we compare the composition of the solution of hydrochloric acid and the solution of acetic acid, in the solution of hydrochloric acid, it exists in the form of hydronium cations and chloride anions. In a solution of weak acetic acid, it exists mostly as molecules with a few acetate anions and few hydronium cations. Now, strong bases are formed by the metals from the groups 1A and 2A, not all from 2A. So this is the list of 6 strong bases which you should know. They dissolved in water, they dissociate completely into cation and hydroxide anion. Next, we're going to talk about equilibrium. The concept of chemical equilibrium is crucially important to understand human physiology. For instance, in the transport of oxygen, the equilibrium exists between hemoglobin, oxygen, and oxyhemoglobin, which is demonstrated by this equation. At the high altitudes, due to the much lower concentration of oxygen, hypoxia can ensue due to the low levels of oxyhemoglobin in the blood. So we're going to learn about Le Chatelier principle. So in reaction that is in the equilibrium, two reactions are taking place, and the reaction proceeds in the forward and the reverse direction. So here you can see two reactions being essentially this reaction being reversed to this reaction. So when is equilibrium reached? Equilibrium is reached when there are no further changes in the concentrations of reactants and products. And at equilibrium, the rate of the forward reaction and the rate of the reverse reaction are equal. You can see here the illustration that, first of all, the rates of the reactions are the same, and the levels of products and the levels of reactants at the equilibrium stage do not change. So in Le Chatelier principle, we describe the changes to the reaction conditions when we change the concentration of reactant or a product. So when we alter the concentration of reactant or a product in a system that exists in the equilibrium, the rates of the forward and reverse reactions will change, stopping being equal. Equilibrium essentially becomes under the stress. And the principle of the French chemist Le Chatelier states that when equilibrium is stressed, disturbed, the rates of the forward and reverse reaction change in such way so they can relieve the stress, the disturbance, and reestablish equilibrium. So for instance, here water in two tanks exists in equilibrium. If we add stress to the system by adding water to the tank A, new equilibrium will be reached, so more water will go into the tank B. So let's take a look at the equilibrium reaction between hydrofluoric acid and water. We're going to consider that this reaction is at equilibrium. When we add hydrofluoric acid, that increases the concentration of hydrofluoric acid in the system, putting the stress on the system. How can we relieve that stress? The rate of the forward reaction will be increased to reduce the amount of hydrofluoric acid, and we will thus bringing the system back to the equilibrium. So adding more reactant causes the system to shift the direction towards the products until equilibrium is reestablished. If we remove some of the hydrofluoric acid, the rate of the reverse reaction will be increased to compensate for that change. So removing some of the reactant shifts the system towards the reactants, increases the rate of the reverse reaction until equilibrium is reestablished. Now, in terms of the products, if we add more fluoride in order to reduce the increased concentration of fluoride, the rate of the reverse reaction will be increased. An addition of more product causes the system to shift towards the reactants. And finally, obviously, the removal of the product will, if we remove some fluoride, it will reduce the concentration of fluoride, shifting balance towards the products. So we can say that the removal of a product shifts the system towards the direction of the products. So this is the summary that you definitely should review. I'm going to be asking about that, and we're going to move on to some link to human physiology. In this equilibrium reaction, the high levels of oxygen correspond to high levels of oxyhemoglobin right here. So that happens in the alveoli of the lungs. In the tissues, the concentration of oxygen is low, thus the reverse reaction allows hemoglobin to release oxygen towards the tissues. So at really high elevation, the person receives much less oxygen than at the regular elevation, may experience hypoxia. So what happens? The concentration of oxygen is very much reduced, so in the lungs it will shift the system towards the direction of reactants to reestablish equilibrium, thus reducing the amount of oxyhemoglobin and reducing the transport of oxygen to the tissues. Now let's talk about dissociation of water and the concept of pH. So water can dissociate, forming hydronium ion and hydroxide ion. And generally speaking, when concentration of these two ions are balanced, we have a neutral solution, and there is more hydronium ion, it's an acidic solution, and there is more hydroxide, it's the basic solution. So water is considered to be amphoteric. It can act as an acid, which we saw in the situation with ammonia, and it can act as a base, which we saw in the situation with hydrofluoric acid. So in pure water, hydrogen is sometimes transferred from one water molecule to another, forming hydronium ion and hydroxide ion. So hydronium ion acts as an acid, so this is one conjugate acid-base pair, water and hydronium ion, and another conjugate acid-base pair is water and hydroxide. So in pure water, the concentrations of hydronium ion at equilibrium, hydroxide ion, 25 degrees Celsius, each are 10 in the power of negative 7 mole per liter. So-called the equilibrium constant for water is the product of multiplication of these two concentrations. And this equilibrium constant is 10 in the power of negative 14 at 25 degrees Celsius. So the sign product constant for water, we just defined it, okay, and usually it is written without any concentration units. So this ion product constant is a constant. So the product of multiplication in any water solution, product of multiplication of concentrations of hydronium ion and hydroxide ion will always be, no exceptions, this number, 1 multiplied by 10 in the power of negative 14. And as we mentioned, when concentrations of these two ions are equal, solution is neutral. If concentration of hydronium ion is greater than the concentration of hydroxide, solution is acidic. If the concentration of hydroxide is greater than the concentration of hydronium ion, the solution is basic. Therefore, if we know the concentration of, say, hydronium ion, we can use ion product constant of water to calculate the concentration of hydroxide and vice versa from that exact equation. So here, pure water is neutral, the concentrations of these two ions are equal. In acidic solutions, as we mentioned, the concentration of hydronium ion is higher than the concentration of hydroxide, but the product of their multiplication will still be ion product constant of water. In basic solution, the concentrations of hydroxide ion is higher than the concentration of hydronium ion. So we already saw this graph. Just to summarize our observation. So now let's take a look. Neutral solution. These are concentrations of hydronium and hydroxide ion and the ion product constant for water. In acidic solution, let's say 1 multiplied by 10 to the power of negative 2. Therefore, the concentration of hydroxide ion has to be 1 multiplied by 10 to the power of negative 12 to achieve that same ion product constant of water. Another example for basic here. If the concentration of hydronium ion is 1 multiplied by 10 to the power of negative 8, the concentration of hydroxide will be 1 multiplied by 10 to the power of negative 6, so the ion product constant of water remains the same. How do we calculate? Well, here's a relatively simple example. So we know the concentration of hydroxide in the solution is 5 multiplied by 10 to the power of negative 8. We need to know the concentration of hydronium ion. Write the equation and figure out that hydronium ion, its concentration is equivalent to ion product constant divided by the concentration of hydroxide. So ion product constant divided by the concentration of hydroxide ion gives us the concentration of hydronium ions. Now we can compare the concentration of hydronium ions, which is this, 2 multiplied by 10 to the power of negative 7, the concentration of hydroxide ion. We see that concentration of hydronium ion is higher than concentration of hydroxide ion, which means that solution is acidic. To measure the acidity of the solutions, we use pH scale. So everything below 7 is acidic. Values for pH usually range from 0 to 14. Neutral is at value of 7, and basic is at value of greater than 7. Now, what do we exactly measure? In some way, we show the negative exponent of the concentration of hydronium ion. So for instance, neutral solution, the concentration of hydronium ion is 1 multiplied by 10 to the power of negative 7. By taking exponent here, negative 7, and making it more negative, adding 1 minus, pH is 7. If its concentration is more than 10 in the negative 7, then pH is going to be less than 7. If concentration is less than 10 in the power of negative 7, the pH is going to be more than 7 for basic solution. It's usually measured by pH meter or pH paper. So here you can see pH meter. It's the most reliable way. Here's the pH paper, which will change color according to pH. This is the solutions of different indicators that respond to different pH values. So everything that is lower than 7, you can see lower than 7, is acidic. Everything that higher than 7 is basic. 7 is neutral. So how can we calculate the pH of the solution? pH is a logarithmic parameter. So pH is essentially a negative logarithm the concentration of hydronium ion. So we take negative powers of 10 in the molar concentrations of hydronium ion, and we convert it into positive numbers. So for instance, here we take the negative powers of 10 minus 2 and convert it into positive number, which is going to be 2. How do we calculate the number of significant figures in the pH? The number of decimal places in the pH value is the same as the number of significant figures in the coefficient for hydronium ion concentration. And the number to the left of the decimal point is the value, so is the power of 10. So 1.0 multiplied by 10 in power of -2 would give us pH 2 digits past the decimal point. Now, pH is a logarithmic scale, which means change of one pH unit corresponds to a 10-fold change in the concentration of hydronium ion. As concentration of hydronium ion increases, pH decreases. Now, you see, this is 10 times higher than this, and this is 10 times higher than this. pH changes by 1 unit. 4, 3, 2. So how can we calculate the pH of this solution? So for instance, we know that the solution of aspirin has a concentration of hydronium ions 1.7 multiplied by 10 in the power of -3. What's the pH? So we know that pH is a negative logarithm. So we write down this expression, then, do it all on the calculator, and calculator gives us this number. Now, how many? So we enter the parameter, then we take logarithm, and we change the number, the logarithm. So the negative logarithm of that concentration of hydronium ion is 2.769 blah blah blah, all these numbers. How many significant figures? In the original concentration of hydronium ion, we have 2 significant figures. This is an exact number, which means number to the left of the decimal point is exact, and it's 2, and number of decimal places is the same as the number of significant figures, 77. We round it up to this number. So you should be able to calculate the pH from the concentration of hydronium ion. Just like we can calculate pH from the concentration of hydronium ion, we can do the opposite. Basically, since pH is the negative logarithm, the concentration of hydronium ion can be calculated by writing this little equation, 10 to the power of negative pH. Okay, you can use a calculator. Here's some table that compares concentrations of hydronium ion, hydroxide ion, and corresponding pH value. Now, acids and bases can react with each other. In human body, there's an acidic milieu in the stomach. So gastric acid contains hydrochloric acid, which is produced by parietal cells. Hydrochloric acid is secreted until pH in the stomach is 2, which is the optimum pH for digestion. Acids react with metals, producing salt and hydrogen gas. They react with bases, producing salt and water. And they react with bicarbonate, as well as carbonate ions, producing carbon dioxide. So that brings us to the definition of salt. Salt is the compound that consists of ions, but does not have hydrogen as the cation or hydroxide as the anion. So first of all, acids react with metals, such as this line, producing hydrogen gas and a salt. Hydrogen gas and a salt. When acids react with carbonates and hydrogen carbonates, so carbonate and hydrogen carbonates, they produce a gas, CO2, a salt, and a water. When acid reacts with base, this reaction is called reaction of neutralization. So salt is formed, and water is kind of a byproduct of this reaction. So in neutralization reactions, one hydrogen always reacts with one hydroxide anion. So, for instance, here, strong acid, hydrochloric acid, completely dissociates into hydrogen and chloride ions, and strong base, sodium hydroxide, completely dissociates into sodium and hydroxide ions. So, these two react, forming water, and sodium and chloride ions exist in the solution in the ionic form. So how do we balance the equations for the neutralization? For instance, we take here magnesium hydroxide reacting with nitric acid. So salt that is formed will be, so first we balance the hydrogen in the acid with a hydroxide in the base. Okay, so we need two hydrogens to interact with two hydroxides, which gives us two molecules of water. Finally, after it's all balanced, we can write down the remainder. So it's going to be 1 magnesium and 2 nitrate anions, resulting in the magnesium nitrate. So neutralization reaction is the basis for action of antacids, substances that used to neutralize excessive acid in the stomach, and usually made out of aluminum hydroxide and magnesium hydroxide. These hydroxide aren't too soluble in water, so the levels of hydroxide ion can be damaging to the digestive system. So here's some components of different antacids: calcium carbonate, magnesium hydroxide, aluminum hydroxide. Now, last topic will be the buffer. The role of a buffer solution is to maintain the pH by neutralizing small amounts, and that is important, small amounts of added acid or base. So you see, if we add acid or base to the buffer, the pH doesn't change dramatically. In order to neutralize small amounts of acid or base, in buffer itself the acid must be present to react with hydroxide ions added, and a base must be present to react with any hydronium ions added. So, for instance, if you take just water and add acid or base, pH changes significantly. But if you, instead of water, use buffer, pH does not change much. So how do buffers work? They can resist changes in pH because they can absorb hydronium ion or hydroxide ion from foods and cellular processes and maintain pH. Buffers are essential for proper function of the cells in the blood, and pH that is maintained by buffers in the blood is close to 7.4. If pH in the blood is changed, it may affect processes like uptake of oxygen, transport of carbon dioxide, functioning of kidneys, and even cellular processes. A buffer solution contains a combination of two acid-base conjugate pairs, and it usually contains a weak acid and a salt of its conjugate base. For example, we have weak acid, which is acetic acid, and its salt, which is its conjugate base. The concentration of a weak acid and its salt usually equal. So, for instance, we have sodium acetate as the conjugate base and weak acid, acetic acid, in the solution. So salt produces sodium ions, which are of no interest for us, and acetate ions, which serve as the conjugate base. Okay, so why we need salt? We need salt to create a large amount of conjugate base, because dissociation of weak acid is not sufficient to generate large amounts of conjugate base. Now, what happens when base is added to the buffer? So weak acid here in the buffer neutralizes the added base. So it creates an acetate ion, which adds more to the pool of the conjugate base and a molecule of water. Acetate ion, on the other hand, can neutralize acid. Okay, so you can see that acetate ion when it interacts with acid, forms acetic acid, slightly increasing its concentration. So basically, buffers work since the weak acid neutralizes bases and conjugate base neutralizes acid. So this buffer, the acetate buffer, works because we provide pretty much equal concentrations of acetic acid and its conjugate base, acetate ion. When we add acid to the buffer, acid reacts with acetate ion. When we add hydroxide, hydroxide interacts with acetic acid. pH is maintained not indefinitely. The added amounts of acid or base should be small in comparison to the concentration of the components of the buffer. If we basically try to dump the equivalent, like comparable amounts of, I don't know, sulfuric acid, buffer won't be able to maintain pH. So acids and bases, here's the concept map for equilibrium. You can use it to study, and the exam is going to be pretty soon.